Imagine this. We gather all the water on Earth, every ocean, every lake, every drop of rain, and somehow transport it to the sun. This is no small feat, considering the sheer volume of water on our planet. Earth's surface is 71% water, and the oceans alone hold about 1.332 billion cubic kilometers of it. Now picture all that water, in one colossal wave, making its way through the vast expanse of space towards the sun. What would happen? Would it be like a drop of water in a hot pan, sizzling away into nothingness? The immediate reaction might be a violent one, with the water vaporizing almost instantaneously due to the sun's extreme heat. The sun's surface temperature is around 5,500 degrees Celsius, hot enough to turn any water into steam in a fraction of a second. Or would it be something far more dramatic, a cosmic event with repercussions across the solar system? The introduction of such a massive amount of water could potentially trigger a series of reactions, both physical and chemical, that we can only begin to imagine. The sheer scale of this event would be unprecedented, a spectacle of cosmic proportions. The answer, as with most things in astronomy, is a fascinating blend of the mundane and the extraordinary. While the initial reaction might seem straightforward, the long-term effects could be far more complex. The sun, a massive nuclear furnace, operates on principles that are both simple and incredibly intricate. At first glance, it seems absurd to think that our tiny planet's water could have any noticeable effect on a star the size of the sun. The sun's mass is about 333,000 times that of Earth, and it contains 99.86% of the total mass of the solar system. In comparison, Earth's water is a mere drop in the cosmic ocean. After all, the sun is a giant ball of burning gas, a nuclear furnace dwarfing Earth in both size and power. Its core is a seething cauldron of nuclear reactions, where hydrogen atoms fuse to form helium, releasing vast amounts of energy in the process. This energy radiates outwards, powering the sun's immense heat and light. Yet, the universe is full of surprises, and the interaction of even seemingly insignificant elements can have profound consequences. The introduction of water to the sun could lead to unexpected phenomena, driven by the complex interplay of physical forces and chemical reactions. To understand the potential impact of this hypothetical scenario, we need to delve into the heart of the sun to understand the very forces that make it shine. The sun's core is where the magic happens, where nuclear fusion transforms hydrogen into helium, releasing energy that powers the star. Only then can we grasp the true scale of the cosmic drama that unfolds when water meets star. The sun's immense gravitational pull, its searing heat, and the intricate dance of particles within its core all play a role in determining the outcome. This hypothetical scenario, while fantastical, offers a glimpse into the awe-inspiring complexity of our universe. The sun, our local star, is a magnificent celestial being. It has been shining down on our planet for over 4.5 billion years, providing the energy necessary for life to thrive. But have you ever wondered about the journey of a star from its birth to its eventual demise? The sun is a giant ball of mostly hydrogen and helium, held together by its own immense gravity. This gravity is so strong that it keeps the entire solar system in its grasp, with planets, moons, and other celestial bodies orbiting around it. Deep within its core, a process of unimaginable power unfolds: nuclear fusion. This is where the magic happens, where the sun's energy is born. Here, under unimaginable pressure and heat, hydrogen atoms are forced to fuse together, creating helium and releasing a tremendous amount of energy in the process. This energy is what makes the sun shine so brightly and provides the warmth that sustains life on Earth. This energy, radiating outwards in the form of light and heat, is what sustains life on Earth and illuminates our corner of the cosmos. Without the sun's energy, our planet would be a cold, lifeless rock floating in space. But the sun, like all stars, is not immortal. It has a lifespan, marked by distinct stages of evolution. These stages are a testament to the dynamic and ever-changing nature of the universe. The life of a star is a complex and fascinating journey, from its birth in a cloud of gas and dust to its eventual death. Each stage of a star's life is characterized by different processes and phenomena, all driven by the forces of gravity and nuclear fusion. Currently, the sun is in its main sequence, happily fusing hydrogen into helium. This is the longest and most stable period in a star's life, lasting for billions of years. During this time, the sun maintains a delicate balance between the inward pull of gravity and the outward pressure of nuclear fusion. But as it ages, the hydrogen fuel in its core will begin to deplete. This depletion will cause changes in the sun's core, leading to a new phase in its life. This depletion will lead to a new phase in the sun's life, one marked by expansion and cooling. As the core contracts, the outer layers will expand, and the sun will become a red giant. The sun will swell into a red giant, engulfing the inner planets, including Earth, in its fiery embrace. This dramatic transformation will mark the end of the sun's stable main sequence phase and the beginning of its final stages. Eventually, even the red giant phase will come to an end. The sun will no longer be able to sustain nuclear fusion in its core, and it will begin to shed its outer layers. The sun will shed its outer layers, creating a beautiful and ethereal planetary nebula. This process will leave behind a dense, hot core known as a white dwarf. This stellar remnant will slowly cool over billions of years, eventually fading into a cold, dark cinder. The white dwarf will no longer produce energy, but it will remain as a silent witness to the sun's glorious past. This is the ultimate fate of our sun, and indeed of many stars in the universe. The life cycle of a star is a reminder of the impermanence of all things, and the constant cycle of birth, life, and death that defines our cosmos. As we look up at the night sky, we are witnessing the stories of countless stars, each with its own unique journey and destiny. Now let's return to our thought experiment. Imagine we somehow manage to transport all of Earth's water to the sun. This includes every drop from our oceans, rivers, lakes, and even the moisture in the atmosphere. Picture this colossal volume of water, which sustains all life on Earth, being whisked away in an instant and directed towards the sun. What happens when this vast quantity of water, representing life and vitality on our planet, meets the unimaginable heat and fury of a star? The sun, a massive ball of burning gases, primarily hydrogen and helium, with temperatures reaching millions of degrees at its core, is an environment so hostile that it defies our everyday understanding. The initial impact would be underwhelming. Despite the sheer volume of water, the sun's immense size and energy output would dwarf this addition. The sun is vast, 1,000,000 times the volume of Earth. To put it in perspective, if the sun were a basketball, Earth would be about the size of a small pea. This comparison helps us grasp just how insignificant our planet's water is in the grand scheme of the solar system. Even all our oceans, poured onto its surface, would be like a single drop of water in a raging inferno. The sun's energy output is so immense that it would barely notice the addition of Earth's water. The water wouldn't extinguish the sun, not even close. The sun's nuclear fusion processes, which convert hydrogen into helium, releasing vast amounts of energy, would continue unabated. In fact, it wouldn't even touch the surface in the way we typically imagine. The sun's outer layers, known as the corona, are incredibly hot, with temperatures reaching millions of degrees. Instead, the water would be instantly vaporized by the sun's intense heat, turning into superheated steam long before it even reached the photosphere, the visible surface of the sun. This transformation would occur almost instantaneously, as the water molecules are subjected to extreme temperatures. This steam, now a mixture of hydrogen and oxygen atoms, would be caught in the sun's powerful gravitational pull and drawn into its atmosphere. The sun's gravity is so strong that it can capture and hold onto these atoms, pulling them deeper into its layers. But here's where things get interesting. The sun's atmosphere is a dynamic and turbulent place, with constant movement and interaction of particles. While the water itself wouldn't extinguish the sun, its constituent atoms, hydrogen and oxygen, would be added to the sun's already potent fuel mix. Hydrogen, being the primary fuel for the sun's nuclear fusion, would find a new home in the sun's core, contributing to the ongoing fusion processes. This seemingly insignificant addition would actually have a subtle yet profound impact on the sun's behavior. The introduction of additional hydrogen atoms could slightly alter the rate of fusion reactions, while the oxygen atoms might participate in complex chemical interactions within the sun's outer layers. Though these changes would be minuscule in the grand scheme of things, they remind us of the interconnectedness of the universe and the delicate balance of cosmic forces. The addition of Earth's water, or rather the hydrogen and oxygen it's composed of, wouldn't extinguish the sun. Instead, it would have the opposite effect. It would make the sun burn even brighter. Remember the process of nuclear fusion happening in the sun's core? The hydrogen from Earth's water would provide a tiny but noticeable boost to this process. This boost wouldn't be instantaneous, of course. The hydrogen and oxygen from Earth's water would first need to mix with the sun's existing material, a process that could take thousands, if not millions of years, due to the sun's immense size and turbulent nature. But over time, this extra fuel would contribute to the sun's overall energy output. The sun's luminosity, the total amount of energy it emits, would increase slightly. This increase might be imperceptible to us on Earth, at least initially. But over astronomical timescales, even a small change in the sun's luminosity can have significant consequences for the planets orbiting it. For Earth, a brighter sun would mean a hotter planet, potentially pushing our already fragile climate towards a dangerous tipping point.